Hi guys, and welcome to lecture 3. We're going to talk about potential energy diagrams in this lecture, and then you are going to look at some, and then you're going to make your own. So, potential energy diagrams. So, first off, the thing to know is that all reactions start with reactants. We know that, and we kind of drew those last time, right? And they all start off at what is called the heat of reactants level. So remember this diagram from last time where we just had reactants and then we had products and we just went up or down. Remember that? So we're still looking at something very similar to this. Okay? So all reactions are going to start with what is called the heat of reactants level. So that's wherever this is, where like here it's the AB, right? Wherever your reaction starts. And then all reactions, even those that release energy, require some energy to get started. And that's kind of the problem with this graph that we did last time. Last time we didn't talk about, well, what does it take to turn the reactants into products? We just kind of pretended like it was a straight shot. Well, the truth is that it's not a straight shot. It actually requires a little bit of energy to give it the oomph it needs to go. Otherwise, everything would constantly be reacting, right? So instead of a straight shot, what we know is that actually all reactions require a little bit of energy to get them to go. And that energy to get them to go is called the activation energy. And that activation energy kind of provides a barrier between the reactants and products, right? That's the energy that is required to have all of those effective collisions. And so it raises the potential energy of the reaction up to this top level where the heat of the activated complex is. So let's take a look at a graph so you can see what I'm talking about. Okay. So here we have another one. This one's exothermic, right? And so again, last time we just went straight down from the reactants that were here to the products, ignoring the fact that it actually takes an effort to go from here to here. Okay. We have to get over this hump. Okay. So up and over this hump is what we're talking about. And the activated complex actually exists right up here. I'm going to give you a big labeled one on a slide coming up. Right now, we're just kind of talking about it. But the activated complex is right here. And this is where those molecules are stuck together. Remember, we talked about how they have to hit with enough energy and the right orientation. And if they do, they kind of stick together and they're getting ready to be products. They're not products yet, but they're getting ready to be products. So if they get enough energy to get up and over this hump, they've absorbed that energy from the collision and they're about ready to react. Okay. So that's where we need to get, right? Is we need to get up and over that hump so that we can then come down and make our products. Okay. So let's take a look at a big one. Here we go. That has all of these words in it at the same time. Okay. So how do you read one of these graphs? Well, remember that the reactants are going to be always the starting point. Okay. So here our reactants are right here, right? Products are always what is made, so this is our ending point. So in this particular graph, our reactants have a potential energy of 40 kilojoules. Okay. Our products are down here, follow that dotted line, see here's our products, down here at 20 kilojoules. So that's comparing our reactants to our products. Now, if you think about what we learned last time, if we go back and make this a really simple one, we're just going 40 to 30, right? That's going downhill overall. So downhill overall means that energy is being released. This is an exothermic reaction. So our delta H, remember that our delta H is products minus reactants. So our products were 20 kilojoules and our reactants were 40. So 20 minus 40 is negative 20 for our delta H value. Negative means exothermic, which is what this little picture helps me see. So this is an exothermic reaction. Now, on this graph, we can label the delta H. The delta H is the difference between the reactants and the products. So it is basically going from, I'm just making this line a little darker here so we can see it. It's the difference from the reactants to the products. So that is our delta H. Okay. Now, activation energy, that's the energy that we need to slam together to make these reactants turn into products. The symbol for activation energy a lot of times is a big E with a little a, right? And so this is the energy that's required to get started. So that's how much energy the reactants have to absorb to make that transition activated complex. So on this graph, what we're going to do is we're going to look at how much extra energy did these reactants need to get over the hump. So they need to get to the top of the hump from where they started down here at 40. So they need to go up to 100. Now, is the activation energy 100? No, it's not. The activation energy is the extra energy. So I go from 40 to 60 to 80 to 100. So that's 20, 40, 60 extra kilojoules is needed. So I'm going to have to put in 60 kilojoules of energy to get A and B to stick together to make that transition state or that activated complex. Okay, it's not a reactant, it's not a product. It exists right here at the top of the hill. Now, this is the symbol for the transition state or the activated complex. It kind of looks like an old school telephone pole. That's just what it is. Okay. So this is telling me that if I have my reactants at 40, if I absorb 60 kilojoules worth of energy during my collisions, I will then be able to stick together and the reaction will proceed to make products. And my products are going to be down lower energy than my reactants, a difference of 20, so this is an exothermic reaction. So there's a lot going on here, but really all we're doing is reading off the graph. Now there's one more thing on this list here that we haven't added, and that is a catalyst. So let's talk about a catalyst here for a second. Get another color for us. How about we do purple? So remember that a catalyst is not a reactant, it's not a product, but it helps to speed up the reaction. Okay, that still looks blue, doesn't it, guys? So it helps to speed up the reaction. It doesn't change the energy of the reactants. It doesn't change the energy of the products. The only thing it does is it provides a lower energy pathway. Remember the mechanism discussion that we had? The lower energy pathway. So rather than having to come all the way to the top of the hump, it only has to go a little lower. So I'm going to put it in here with a dotted line since the purple looks kind of the same. Okay, so that dotted line is the lower energy pathway that the catalyst provides for us. And if we have a lower energy pathway, then we also have a lower activation energy requirement because now we're not having to go up as high. So we can figure out the activation energy when you have a catalyst the same way, right? We're going from the starting point to the top of the catalyst. So the EA with the catalyst should be less. Okay, so let's see. That's 20, that's 40, and not quite halfway, so let's just estimate it to be 45. Okay, so the activation energy, if I have a catalyst, is only 45 instead of 60. So this is how you read one of these diagrams. There are different areas that are going to be labeled or that you will label as reactants and products and delta H and activation energy and transition state and catalyst. So a couple of words before we go into making our own. A lot of our exothermic reactions are going to be what are called self-sustaining. And what that means is that once they get going, you don't have to keep on putting energy in. And that is because even though they have to get over the hump, right, because they are exothermic, what happens, remember, is that they are releasing energy. So as they go over the hump and they make products, energy is released out into the atmosphere or the surroundings, and that energy is basically recycled back to help the reaction go some more. So it's kind of cool. Exothermic reactions tend to be self-sustaining. This is, think about lighting a match, right? You give it that first strike of the match to grind everything together, give it a little bit of kinetic energy, and then once the match is lit, the match continues to burn. And that's why the energy that is released in the form of the flame, right, then proceeds to get recycled so that the match doesn't have to continually be re-struck against the box. So exothermic reactions are often self-sustaining, which is kind of cool. And then the other thing is the forward and reversed equations of the same reaction, like synthesis and decomposition. The diagrams are mirror images. Now that's a lot of words. So on the next slide, I'm going to show you side by side an endo versus an exo, so you can see what I'm talking about. So these are not on your paper, but if you want to add them, you certainly can. But this is trying to help you pull together some of these ideas from lecture 2 and then from this new lecture. So here we have an exothermic reaction like on the previous slide, right? So they're not very well drawn, but these are the ones I found. So reactants are here. We have to get up over the hump, so that's our activation energy, right? Whatever that value is, and then we make products. So this one, delta H, is going to be less than 0 because I'm taking a small number minus a big number. So it's going to be negative. That's, again, how I know it's exothermic. If I take this same graph and I basically flip it around, right, now my reactants are down low and my products are up high. So this is an endothermic. So you can see if there was a mirror here, it would be like a mirror image. Endothermic, big number for products minus a little number for reactants. Delta H is positive. So here we've got our activation energy to get over the hump. And then for endothermic, you'll see it takes a good bit more for this reaction to get over the hump. Not always does it take more, but in this case it happened to. And the delta H is still the difference between the reactants and the products. And this is one, let me erase all these marks. This one has marks on a few different places, and I think it's important to move these marks around just to show you, because you don't have to label delta H under the reactants like it is on this one on the right. You can do it underneath the hump. Really, I mean, what you're really always doing is taking the difference between the reactants and the products. And this is true of the activation energy too. A lot of books label it under the hump. Both of these are labeled under the hump, but you don't have to label it under the hump. It's the energy it takes to go from the reactants to the top of the hill. So there's no reason you couldn't label it here as well, as long as you stopped your arrow at the height of the peak of the hill, right? So you have to be comfortable with the fact that you can label them in a lot of different places. Okay. Same thing with delta H's and the transition states. I could put the delta H even over here if I continued this out. Okay, so delta H is just the difference between these two, and activation energy is just the energy it takes to get there. All right, so this one is not in your notes, so don't put this one on the big graph that's in your note packet. Maybe do this one on separate paper, or there might be room like down at the bottom or something, but this one's not for the big blank spot on your paper. This one is for me to walk you through how to do it, and then you're going to do the one on your paper. So this one's different, okay? So for this one, let me get a black pen. Here's the reaction. NO2 goes to N2O4. So we have to look at all of these different things. So this is telling me that NO2 should be at 30. NO2, that's the reactant, so at 30. Oh, I forgot to put numbers on here, guys. Okay, so let's see, 5, 10, 15, 20, 25, 30, 40, 40. Yeah, I'm going to put these on by 5. I don't know how I got this on the slide without any numbers. It's kind of weird. Okay, so here we go. I'm just labeling it so they're there for us. Okay, so delta H of NO2, so that's the potential energy for the NO2, should be at 30. That's right here. So I'm going to draw a line kind of as my starting point, and I'll put my reactant on it. And then for the product, it should be at 10. Okay, well, that's down here. So I can already tell that this is going to be an exothermic reaction because the energy went down, all right? But I have to put in, oh, I didn't make my graph big enough. Let's see, did I? Activation energy of 40. I made my graph not big enough. 5, 10, 15, 20. Oh no, 25, 30, 35, 40. It goes way up off the slide. And okay, here we go. Let's say it goes way, let's pretend that's 40. It's too hard to start the whole thing over. So if this is 30, that means this would have to be up here at 70. Okay, so that's my EA, way up here. Okay, that's an additional 40 kilojoules. So that's how I got the 70. I put 30 plus 40 is 70. That's how I got there. Okay, so I've just sketched my potential energy graph. It says find the values of delta H of the reaction and the transition state. So for the reaction, it's just going to be the difference between the reactants and the products. So they're at 30 and they're at 10. And it's always products minus reactants. So that means that my delta H is negative 20. So I know it's exothermic. Okay. And my transition state, that's up here on the very tippy top of the graph where I can't see it. So my transition state is up at 70 kilojoules. There's my little transition state sign. Okay. And then it says to sketch it if a catalyst is added, lowering the activation energy by 15. So instead of requiring 40, it's going to require only, what is that, 25? Maybe that one will fit on the graph. 5, 10, 15, 20, 25 would be right about here. So here's my catalyst. A lot of times they draw catalyst with a red line. Okay, again, notice I'm kind of blending it in to the already present reactants and products. It doesn't affect those at all. It only affects the height of the hump. So here's my activation energy with the catalyst. Okay. It's only 25. So it's a lower energy pathway. Okay. So this is kind of how we take all of these numbers and we stick them onto a graph. So you guys have one in your note packet. Here's the great big numbers. Again, for some reason, this got away from me without any numbers on it. So we're going to, I'm going to add these in here. We're going to hit pause, or you're going to hit pause if you're doing this at home. And I want you to draw the sketch in your notes. And then once you get the sketch drawn in your notes, you can unpause this and you can see if you did it correctly and kind of see how it unfolded. So make sure that you hit pause and that you make an attempt to do the one that's in your notes and then come back here and check. Well, guys, I totally didn't tell you the truth. That this one in your notes is the same as the one on the previous slide. So if you already wrote it down, you figured that out. If you didn't write it down, well, you just got a chance to do it yourself. I totally thought I had changed these numbers for you, and I didn't. But again, this is my completed graph. You can see it's not spectacular, but that's okay. We've got the information that we need on it. We have all of the things that we were asked to have. We have our starting point, we have our ending point, we have delta H, our activation energy with and without a catalyst. We've got our transition state up here at the tippy top for, again, with and then without would be down lower, right? With and without a catalyst. And again, the big thing here is I want you to see it doesn't change delta H to add a catalyst. It's still negative 20 and it's still exothermic. The only thing that it does is it makes it easier to get the reaction going from reactants to products. So here is what you should be doing after this little lecture. Two things. You're going to go to Google Classroom and you'll complete the items with the number 1 next to them. These are just like the ones that we did last week. Several of them are from the CK12 site. There's one on activation energy, there's one on the activated complex or the transition state, and then there's one on the diagrams as a whole. So each one of them is pretty short. So these are the classwork if you are in class, or they are the right now work if you are at home. This lecture was right at 20 minutes long, and they should take you less than the remaining 60 minutes for sure. So you've got plenty of time if you've set aside time for yourself to do your work. Then there's a Google slide assignment where I've made you a blank Google slide that looks like the graph in your notes, and you're going to be sketching a Google slide using the little squiggle tool. So, or you can do it on paper and submit that if you prefer. So you'll be doing the CK12 lessons just like last week. Remember, you have to keep working until the little level says that you are at least proficient to get full credit. And then you will do the making your own Google slide. So that's it for the first part of the week. And then for the last lecture, we will talk about spontaneity, which is another really cool topic. And that'll be it for this week.